Hello, we are February 18th, 2025, and I was really busy doing my I'm just PD work, which is my school work. Okay, I need to close everything here. Um, Today, what I wanted to do was do something different. So, this Saturday or this Sunday, what are we? Tuesday. This Sunday, I went down like a CUDA rabbit hole, and I was gonna do a session two, but then I got sidetracked. And yesterday, I was pretty much out the whole day, so unfortunately, did not make a lot of progress. And today, I was supposed to start streaming a bit earlier, but I had to do some schoolwork with PD, which is professional development, which is really annoying, and it's not that interesting. But anyways, we are now 11:55 p.m. I have to still go to work tomorrow. But there's been this topic that I've always, or that I need to really brush up on, which is segment trees. And I've actually learned a bit about segment trees um, over 2 years ago. And I have this template, but I just like this way of I learned it and it's just like copy pasting code. So I want to like reason it out, like build one from scratch, um, and then reason it out, and then sort of see like how my implementation differs from the actual implementation. So I have a rough idea of how a segment tree works. So we're gonna try implementing it, and we're gonna open warp, go in competitive programming, and then not demage. Let's see here, sorting or data structures. So I'll make a folder data segment tree. So the basic idea of a segment tree, or I think, so there's also Fenwick trees, and I don't know the difference. But basically, you segment trees are really useful for range queries. So imagine the most common example, or simple example. The most simple example would be an array. And imagine your array has n elements. All right. So some elements. Let's say like 5, 4. Okay, let's some random numbers. And you want to query the sum from one index to another index, right? So if your array is fixed, you can just use a prefix sum, where you pre-compute the sum up to index I, and then if you want the index from I to j, that would be the sum to j minus the sum to I minus 1, and then that will give you the sum from I to j. And if it's from 0 to j, then you would just take the prefix of j, right? But that doesn't work when you modify the values, in which case you need to update your prefix sum. So I guess like as a quick example, let's say we have an array, let's just use vectors. So include vector using namespace stud, and then we're gonna do a vector int array, and then let's initialize it with these values, and then now the prefix sum. So the prefix sum from an index I to j, and j return. So if I equals 0, return prefix j, and then this will be prefix j minus prefix I minus 1. So this is how you do a prefix sum. Generally, I would have a global variable like prefix, and this would be size, like whatever size. And then when you have your array, you would just generate your prefix sum. Prefix I equals array at I plus prefix I minus 1, and then I guess we can do this. Prefix 0 equals array at 0. And then we can now compute the prefix sum. So let's say from index 2 to 4 inclusive. We need IOStream here. So something like this. The prefix sum from index 2 to 4, we should expect 2 plus 3 plus 6 is equal to 11. So let's see. Segment tree. So this is just prefix sum. And then we get 11. If we go from 0 to 4, that should be just like the sum of the 4 elements. So the first 4 elements, 5 plus 1, 6 plus 2, 8 plus 3, 11. Oh, 4, index 4 is actually the 5th element, plus 6, 11 plus 6, 17. Right, this is very straightforward. There's a prefix sum. But now if you want to update it, you would have to update your entire prefix sum starting from that index, right? So if you update the value at index 3, then the prefix sum here is in effect. Up to 5 is not affected, up to 1 is not affected, up to 2 is not affected. But the prefix sum up to index 3 is affected, prefix sum up to index 4 is affected, etc. Right? So anything that follows that value, that prefix sum needs to be updated. So in the worst case, it's O of n. So instead of that, we can sort of like think of an idea, right? So this is O of 1, and pre-computing is O of n. So your generation, your first time you generate it is O of n, and then your lookup afterwards is always O of 1, right? But you cannot do an update. If you do an update, then it's going to be O of n. All right, so you get O of n for prefix array, prefix sum. You get O of n update, O of 1 lookup. So an alternative would be to figure out a way to do a O of log n update and then a O of log n lookup. So to think of how this works, right? And again, I'm just like basing it off just my imagination. So this is might not be entirely correct, and we're gonna figure out what the actual implementation looks like at the very end. So let's create a new drawing, and sort of like this is. And partially, I remember learning this, but I don't know in terms of implementation how it looks like, right? So imagine like you have an array, and these are your elements. All right, these are your elements, and then just have a bunch of these. And we're going to make it a multiple of, how many should we do? 8 or 16? 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's just do 8. So let's say you have 8 elements. And the idea is that we're going to have this be represented by nodes. So initially, these are like nodes. Okay, there's like values here. 5, 4, oh my god. 1, 10, minus 3, 4, it's 8, 11. Okay, these are a bunch of values, right? And what we're going to do is store a sum, because we can use rectangles. We're going to do something like this. So you'll have, let's say this is an array of size n. What you're going to do is you're going to start with n nodes representing each of these elements. And then one layer up, you're going to store the sum of 2 nodes. All right? Like that. And then one layer even higher, you're going to store, so this would be 9. This would be 11, this would be 5, and this would be 13. And then one layer higher, you're going to have the sum of these, So this would be 18, and this would be 20. And then finally, your root node would represent the sum over the entire array. In this case, it would be 20 plus 18 equals 38, right? And so this would represent, and then like we need to, I'll just keep track of like 0 to 1. This is 0 to 1. This is 2 to 3 inclusive. And then this would be 0 to 3 inclusive. And then this would be 0 to 7. 7, and then this is 4 to 5. And this is 6 to 7. And this would be 4 to 7. And then you get 0 to 7. And so with this setup, now we can think of it as we've sort of like split it down into powers of 2, right? And how this is useful to us is when we want for updates and queries, right? Because it is this sort of tree structure, the height of this tree is going to be at most log n, right? So if you sort of like, first of all, picture how many nodes there are. So the height of this is log n, just by like, this is how a tree works. The height of a tree is always going to be log n. And then your root, this layer has n nodes. This layer has n or less nodes, etc. So your total number of nodes will be bounded by O of n log n. Okay, so there's O of n log n nodes. And then when you traverse down this tree, you have to traverse at most n or log n levels. Okay. So then let's talk about, and the reason it's log n is sort of like, you can imagine every time, why it's log n is because we're starting from n, right? And then we go down, it's n over 2, right? So if the lowest layer is n, then the layer above that is going to be n over 2, right? Because we're having it every time. This is a binary tree, right? So each node has at most 2 children. So n, then n over 2, then if you divide n, so there's n over 2 nodes on this layer, then the layer above that, you again have it, n over 4, etc., n over 8, etc., until you reach 1, right? Once you reach 1, you stop, right? Because you can't have 1, and this is the root node. So if you then look at what we've essentially done is we've said how many times do we need to have n until it reaches 1, which is the same as saying what is the log base 2 of n, right? I think that's what it means. Yeah, because it's equivalent to saying 2 to the x equals n. What is x, right? That's the log. Because essentially it'd be equivalent to saying if you're having n until it's 1, that's saying like how many times do you need to multiply 2 until it becomes n. Those two are equivalent, right? And so then that's the logarithm. Anyways, so back to, let's look at how we can potentially do a range query, right? So let's say we query from 3 to 7, or 0 to, if the interval is like right there. So if we query 0 to 3, we start from the root node and we look at, is it, it will for sure be inside within 0 to 7, right? If we query, let's say we're querying 0 to 3, right? In which case we will traverse down here, and then we see that, oh, the left and the right are exactly the same interval, in which case we'll just return this value. We're just looking at query for now. If we have 0 to 4, what will happen is we'll take 0 to 4, we explore down the left, right? And 0 to 4 fully spans 0 to 3. So then we're going to take this sum and propagate it back upwards. And then 0 to 4 and 4 to 7, right? In this case, there's a partial overlap where 4 is the only overlap, right? But we don't know, I think this will get clipped to 4, 4, right? And then this will get propagated down, and then this will get propagated down, and then you get minus 3. So it's equal to minus 3 plus 20, right, if we wanted 0, 4, right? And that's exactly the correct answer. It's 20 plus minus 3, because it's 5 plus 4 plus 10 plus 1, which is 20, plus minus 3, right? So this is sort of the logic. Now, you can see the thing that I was had trouble convincing myself was like, okay, it seems like in the worst case we're going to visit all the nodes, right? Like, because there are n log n nodes, but we promised to do this in log n time. So how does that exactly work? Right? Because like when we do 0 to 4, this might span this and might span that, right? So why is it log n? And that's because I'm thinking now. I don't know why. In the worst case, like let's say in the worst case, what happens, right? So you start from the root node, and then and then you look at the children, and it will include both the left children and the right children, right? So it exists both here and here. And then once you're here, you want it to exist both from here and here. However, so if it was 1, 2, right? If it was 1, 2, but like it's not possible. Like, right? There's a contradiction. Like, if you wanted to span both the left and the right child without it cannot fully span 0, 3, because if it fully span like this interval, then you would just return this interval. So it must somehow like span this interval, but not completely. So it could be 0, 2, 1, 2, 1, 3, but not 0, 3, right? But remember that because we visited both the left and the right child, then it cannot be less than the right side, and must be greater than 2. Like, it must be 3, right? Or like it must be 0. Like this side must be 1, 3, right? So the left side must be like 1, 3 must be included in the original query, and then that, if it's 1, 3 included in the original query, this will be visited, and this will be visited, and then we'll stop here, and then this will go down here. So this node will be visited, this node will be visited, and then let's try to figure out a way to have this run the whole time. Yeah, I think 1 to 6 actually, right? So the 1, 6, and let's look like so this one, it gets visited. Sorry. This one gets visited. This one gets visited. This one gets visited. And then this one gets visited. Maybe it's better to use another rectangle. This one gets visited. 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 And then 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 4 to 5 gets visited because... So how many nodes have we visited? There are 8 nodes. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of 10, 11, 12, 13, 14, 15. 9 out of 15 nodes. Which is, n log n would have been 8 times 9, or yeah, 8 times log of 8, which is 24. Wait, what? How many nodes are there? Isn't it n log n? 1, 2, 3, 4, 8 times log of 8. What's log of 8? 2 to the what equals 8 to the power of 3, right? So 8 times 3 equals 24, but there's not 24, are there? 8 plus 4, 12, plus 2, 14, plus 1, 15. How many nodes there a binary tree. Yeah, it's less because I'm doing n times log n, but it's less than n log n. It's like bounded by n log n. Why? Because it's 1 plus 2 plus 4 plus 8, which is just a sum. Sum of 2i, right? Sum of 2 times I, 1 plus 2. No, 1 plus, sum of 2 to the I. What's the sum of 2 to the I? Is the sum of 2 to the I to the k up to k basically 2 to the k plus 1 minus 1? Really? Huh. Subset. It's like subsets, permutations. Sum of I to the k of 2 to the I equals 2 to the 4, 2 to the k plus 1 minus 1. Is that true? It's a geometric series, right? That's because you divide by 1. Okay. Yeah, geometric series. Yeah, I guess this would be n, and then this would be So that should be 2 to the n plus 1 minus 1. To the h minus 1. Yeah. Not n log n. Okay. So that's incorrect. We don't have n log n. So that still gives us the height is 2 to the log n. What do you get when you do 2 to the log 2 of n? Is n, right? 2 to the something gives n. Log 2 of n means 2 to the what gives n. That's your what. And then 2 to the what, that gives you n. So in the worst case, isn't it O of n? Because you might visit every single node. Okay, so I think, yeah, this is the confusion. I don't know why it's log n, but the idea is when you do an update, you would also just visit the nodes that are affected, right? So if you're updating a given number, any interval that includes this number will need to be updated, right? So 6, 7 is not affected, but you just like go up and propagate those values. And because again the height is at most, I guess update makes sense. You only need to go through, like, the path to your root node is log n. You need to visit log n nodes. You don't need to visit other nodes, right? Because the only nodes that are affected are, there's only like one node per layer affected, right? Now 10 only is only included, like the index 2 is only included here and then here and here. So propagation for a single value is only affected once. Can you make an update on a range though? Like, how would that work? Okay, and then let's revisit segment tree. Okay, and this was what I was visualizing, right? Okay, yeah, this is exactly what I drew. Yeah, so I guess because we have 2 to the n, why are we storing just 2n? I'm confused. There are, if an array is n nodes, we only need 2n, but then we just prove it it's, oh. So it's log n, so the height is log n. So log of this number, that's the height. And then it's 2 to the height n minus 1. I'm a little confused, guys. If you have two elements, log 2 is 1. Then 2 to the that plus 1. 2 to that number plus 1, which is the same as 2 times that number minus 1. Okay, I understand why it's 2n. You only need 2n elements. If there are n nodes, you only need to store there are 2n nodes. What? Oh, really? It's none of that complicated stuff that I reasoned about. Two n minus 1 or 2? If there are n nodes, n child nodes, how many nodes are there in total? Okay, well, I would need to think. You have, in the simplest case, you have 1 plus 2 plus 4 plus 8, and oh my god, guys, and it's suddenly getting tired. there's n nodes and an n over 2 nodes and an n over 4 nodes. But that's equivalent to, like, assuming for simplicity that it's a result of a 2 to the x. Right? So you have 1, 2, all the way up to the x equals n. So log n equals x, right? And so then you have, what are you doing? 2 to the I, right? 2 to the 0 plus 2 to the 1 plus 2 to the 2, etc. until 2 to the x, where x is equal to log n. And then that sum is equal to 2 to the log n and 2 to the log n is just equal to n. Plus times 2 minus 1. So if there are 8, then it's 2n minus 1. Okay. All nodes in a binary tree. This was important to reason out, as opposed to taking for granted. First level has 1 node, has two nodes. Has 2 to the I nodes. In total, have 1 plus 2 to the 0 plus 2 to the 1 plus dots plus 2 to the h equals 2 to the h plus 1 minus 1. If the where h is the height of the tree, h approx log n, so we can actually, h is less or equal to log n, so we can actually solve this. 2 to the h plus 1 minus 1 is equal to 2 to the is less or equal to 2 to the log n plus 1 minus 1, which is equal to 2 c dot 2 to the log n minus 1, which is equal to the 2n minus 1. So our 2n minus 1 there are at most 2n minus 1 total nodes, and we need to seal it. Okay, yeah. All right. So once we understand that, why is it that, okay, and then let's go back to our segment tree before we even go to some notes. Actually, CPO with. Okay, isn't that? C of log n. Yeah, okay. If you seal the log n, it might be x plus 1. Where does the 4 come in? It might be 2 to the, it's like m 2 times m plus 1. What is it 4n? 2 times 2n. No. This is n, and this is times 2. 2 to the... That is... Oh my god, why are you complicating this? see. So this one I did not actually spend time trying to reason out. Okay. Yeah. The CO block base 2 of n. I guess the base 2 is important. And the high is just equal to the last layer has 2 to the h nodes. So actually we can solve this. The number of vertices can be estimated by the sum. But I thought like there would be less nodes. Like how is it? How is it? Like I'm not convinced. Like if n is 4 0 0 I see when there's 5 elements, right? So 0 4 oh 0 to 4. I see they split like this. That's an interesting way of putting it. So for odd elements, I guess they drew it like this. I would have like done 0 0 1 1 2 2 3 3 4 4, and then like combine like this, and then 2 3 would be combined, and then 4 to 4 would just be its own thing, and there'd be a node here, and then go up, and then it would go from 0 to 8, I guess. 0 to 3 is not enough, so the next one is 0 to 7. 0 to 7, yeah. Yeah, so this case, it was the case that I could not get my head over it. And it's like, if it's always the worst case, doesn't it just explore everything? In which case, it's like O of n time. So let's try to answer this, alright? Because you need a partial answer from the left and then partial answer from the right. Once or twice, once, and we only visit no more than four vertices. was trying analysis. I was confused how it be log n and not O n, since there is a case where both children need to be visited. The left and right subtrees need to be visited. So in the worst case, are all of their entire tree is visited unless there are O of n log n. A query takes O of n time. Yep. The proof is by induction. Places are visited per level. Since there are log n levels, then the runtime is O of log n. Okay, so how do we prove that there are at most 4 vertices visited? Yes, so our base case, so induction, remember how induction works. So we have a base case for your base case, and then you have your induction hypothesis, and then you use that induction hypothesis to prove the next step. And there's like the strong induction, POSI, principle of strong induction, and that one, guys, I have notes on this. Wow. Damn, look at me. That is, we assume, which stands for, see, I have like the formula right here, guys. Dude, this is so cool. I love my induction note. So why have my notes not uploaded since induction? Look at this. Damn, Steven. Damn. Okay. Induction, right? I remember Eric, yes. 4n or 2n? Because you have some bunch of checks, I assume. Yeah, I think it's fine to just like use pointers instead of like linearizing the array. Um, with the array, it's just like the way you index them is a bit easier. Um, but anyways, we still need to understand why prove that prove norms in. Let's see if ChatGPT uses induction. It's not true that at most 2 nodes are visited, right? I think at most 4 nodes is visited is true. Because here we literally 1/6 visits 4 nodes. So I think this is what ChatGPT said about 2 nodes. But 4 nodes can make sense, right? 1 3, like it's in both. Why is it O of log in? How can you say this? There's more than less 4 or less. By induction hypothesis. Only 2 of these. This is important. assume that we visit 3 or 4 vertices in the current level. Alright, because we are computing contiguous sum, these 4 vertices cannot be disjoint, as in they should be like right next to each other. First, observe that these 4 vertices must be contiguous because we are computing the sum for a contiguous range, right? So then you see that these 2 middle vertices are completely covered, so there is no point of them going further down. Assume by contradiction isn't completely covered, then you'd the leftmost node would be disjoint. You would end up querying a non-contiguous interval. And I think like the update queries is four. So we can use vertex, or we can use an array. And use one indexing. So yeah, building this tree is non-trivial. So, and updating is also not trivial. And like I visualize as you update, you get the child node and you go up. Okay, this is a bad gesture. You go up, but I don't, and then you will be able to do it in login. That's like that's a recursive function. Okay, and then build an update. So use a vector long of segments. Okay, so I'm trying to think how an array implementation work. So okay, let's just reason it out. For a non-array implementation, what we could do is we could, right, whenever we do a query, we just do this recursive. We start from the root, and then we sort of do it down, and then each of these nodes would have metadata information about the intervals, and so you just have some logic to check the intervals, right? And then for update, I would go from bottom up. If you go top down, then you just look at the left or the right and you figure out which ones you need to go down, but how much you update it by, you need to know how much this is, so you need to go down and then go back up, right? So it's like a two-step process. It's like 2 log n. But there's probably a simpler way, and that's what I'm trying to figure out. Like, if I understand this array version, we can maybe do the naive way first, because if you look at it, like, they actually have not much logic to handle the bounds, and it's like, is it that easy? Oh, they have this. So what is this? So when we build it, so what they do is the indexing will be 1 corresponds to the root node, 2 corresponds to, or 2 times 1 is the left child, and 2 times 1 plus 1 is the right child. And then I don't understand why that works. Hmm. I see. So you recursively call in any, it's like a in-order traversal or post-order traversal or pre-order traversal. Yeah, it's post-order traversal. In-order traversal is visiting the left, doing stuff, and visiting the right. Whereas post-order is you visit it, you make sure you visit the left, and then visit the right. And then only when you're done visiting left and right, then you visit the current node. And we do post order traversal. Why was there BFS? Yeah, update is in order traversal, but it's post order traversal, and then getting a query, let's reason it out without looking at the answer. So when we query a number, what we do is we are given a range, and then if the left and right are equal, target and then range. Oh, I don't know what the arguments are even. If TL and then equal, return to V. If else, we will start. You get the medium, which is those two, and then if L is greater. And take a max, I see. The sum plus that sum. Yeah, that makes sense. And then updating is, how does an update work? I believe I have this code somewhere, right? I think Eric though made a video now.
It's up to 32. The question is how to get the. Well, how our tree would change if I said that
I do remember watching this video. Eric Toe.
Welcome to Algorithms Live, Bean. At every stage of the search, this is tracking these kind of problems that you can ignore. Okay.
Yeah, I don't know where I stole this code from. Maybe it was CP handbook. Box. Wait, what? It's in coding? Coding interview, computer programs. Guide to CP, huh? Successors. Oh my god. LCA. Oh my god. Forgot that. Okay, here. And we go second tree. I used to love Bitset. I barely use Bitset now. I don't know where I got the. Actually, this is a Fenwick tree. I remember like learning Fenwick trees, and that was like more intuitive to me. There was oh no, that's not. That's literally the guy I looked up. What's the Java guys? That's not his name. Eric Joe, no. Gennady, no. What's his name? Oh, and the sparse table. Holy crap, man.
to solve the problem on the right with this quite short 40-line code. The problem that we try to solve is called RMQ, range minimum query, where we are given a sequence of numbers and we need to efficiently answer queries given an interval, like from this position to this one, or in the minimum. Here the minimum is 1 as the smallest element. If I ask about those 4 elements, the minimum would be 2. Obviously I can achieve this with brute force in complexity for every query, and let's say there are q of them. I just go through the interval. In the worst case scenario, the length of interval is just the whole sequence, so brute force is q times n, and our goal instead will be to do preprocessing in n times log of n, and then each query will be answered in constant time, not even logarithmic. It's very common that we have here times log, right? But no, with sparse tables we are able to get constant time.
So I think the idea is you do O of n and then log n. These are 2.
And per query. This is our goal for the smallest queries very efficiently. And corresponding to, and I want already in the past to get of 1, 2, like for 20, use this log of n. Log here I just hard coded at the top for simplicity, but you can also like get it after reading n. You could here say log is, and just get in some way log of n. Then answer price. For every query we read L and R, and we run the function. What does the function do? Here we need some way to find the logarithm of the length. Right? I get the length.
Maybe my notes explain this better. Huh. Just I never really used this, so shit, it's 1:15. Okay, I should sleep now. Oh well. At least I tried a little bit. Okay, we can continue this tomorrow. So at least we understand the proof for why there are at most 2 nodes visited. A Fenwick tree is a variation of it. I guess like this rabbit hole for range queries is kind of important. So sparse table is like, it's pretty fundamental, man. Lowest common ancestor is pretty fundamental. don't know where I stole this from. I remember learning Fenwick tree. This guy, second thread.
The rest of your team is COVID positive. Yeah. Good morning, everybody. Problem node. To implement, you gotta be careful with it.
Second thread, Fenwick tree.
So, and 11 has a least significant bit at position 1, so it's only responsible for oneself itself. So, here I've outlined the least significant 6, and then, alright, now the prefix sum for up to 11 non-inclusive.
How do you compute the prefix sum? I'm confused about this. Wait, but I don't understand why it's. Whoa. Do we only really need 2 numbers? Hmm. Okay, alright, I'm gonna stop here. I'm getting confused.